Yeah, only a few minutes of my schedule. So I'm happy to introduce Stephen Diamond. I reached out to Stephen to come give a talk here. He's working on some really interesting things that happen to be in Python, but I think there's a lot that we can learn about modeling concepts and similar problems that we're all having solved either in Julia or in DCP, in Python, and I'm excited to hear about graph-based architecture for modeling frameworks.
Well, thanks, Miles. I really appreciate the invitation. I think it's really cool what you guys are doing with Jump and the community you've put together. It's sort of inspirational in terms of. So I've been working a lot on CVXPy, which is essentially a version of CVX in Python. I guess how many of you have used CVX or something like that before? Okay, so a lot of you. So I'm going to talk a little bit about the general idea with that. But the main subject of this talk is sort of a new approach to designing this whole end-to-end system of modeling language, rewritings, putting into standard form, and then calling the solver. Moving away from an approach that's centered on a sparse matrix representation and moving towards an approach that's based on a graph representation. And I'll explain why this is desirable in more detail, but it opens up, basically it lets you exploit structure and scale that the graph, or that the sparsity-based approach really struggles with. And I think it's going to be an interesting direction going forward for these modeling systems. And this is work I did with others, and my advisor, Stephen Boyd at Stanford. So first, just a few words about convex optimization. So our standard representation of a convex problem is some convex objective, F naught, convex inequality constraints. Okay, so each of these Fi is convex, and then linear equality constraints. Okay, and of course, right. So these can be any convex functions at all. I'll talk more about the standard form that you map it into later. So why is it worth focusing on convex problems? Well, there are a few reasons. One is that the theory is very elegant and well developed. And it gives us things like duality and so forth. And also various algorithms that are very efficient in practice, very robust, and also efficient from a theoretical perspective in terms of computational complexity. So altogether, it's sort of a very, very elegant system of work. And perhaps most importantly, it's a class of problems with a huge number of applications, more than you would think at first glance. You have applications with parameter fitting in machine learning statistics, or what's now called classical machine learning, meaning it's about 10 years old. And you have control. Many control problems can be approached very effectively through convex optimization. Signal and image processing. You get some interesting large-scale problems that I'll talk a bit more about later. Network optimization, like some power flow problems, for example. Engineering design, finance, portfolio optimization. So actually, I have a little personal experience with this. And I won't say too much, but basically, billions of dollars are allocated based on solving these, mostly QPs, but these convex problems. So this is even just with this application, it's a very important class of problems in terms of making the world run. Okay, so how do you solve these problems? Well, the most straightforward approach is to use one of the solvers that people have already developed. And these are intended to be for a wide range of problems. So they have some sort of standard form that you need to convert your problem into. So for example, linear programs, quadratic programs, second order cone programs, semi-definite programs. And so once you have your problem in that form, this is very easy. These solvers are efficient and robust, and you get to amortize that investment in making this a really good solver across all these different applications, all these different users. So that's a fairly useful paradigm. But it doesn't work for every problem. There are some cases where you have structure that isn't exploited by these solvers, or you have a problem that's so large that it doesn't really work with these solvers, or just in general there can be a lot of reasons why these standard solvers don't work for you. And so in that case, you would write your own custom solver, which is obviously a lot more work, but it lets you really get the best possible method for your particular problem. And in between these two approaches, we have the idea of convex modeling languages, which, similar to JUMP, it takes your problem in a very straightforward, user-friendly way that fits with your idea of how the problem is expressed, and then it converts it into these less intuitive standard forms through sometimes quite complex transformations, ideally preserving the structure that is important for solving the problem efficiently. And so this makes these solvers much more useful by extending the reach of the problems that can be solved by these guys with minimal effort. Okay, so now let's look at how this comes together in an end-to-end system. So the first layer is the modeling language, and these go back to AMPL and GAMS in the 70s and 80s. And more recently, there have been a variety of different model languages specifically developed for convex optimization. So starting with CVX and YALMIP, we have CVXGen, which is a code generator, and then CVXPy, which I worked on, and convex.jl, and there's going to be one in R soon at some point. And so these model languages do two important things. One is verify problem convexity. The other is convert the problem into the standard form required by the solver. So the system for verifying convexity that was introduced by CVX and then used by all of these guys, the CVX descendants, is called disciplined convex programming. And so the idea here is that you have essentially almost a type system that you use to infer the curvature of your expressions. And it's a sufficient condition for guaranteeing convexity. It's not a necessary condition, but it's very simple. And it has other benefits related to the standard form that I'll talk about more. So basically the idea is that as these expressions are constructed by the model language, they're tagged with some curvature, whether it be constant, affine, convex, concave, or unknown if the type system fails. And expressions are formed at the leaves by variables and constants and parameters, which are just constants with where you can plug in the value later. And then the intermediate nodes come from a fixed set of functions with defined properties in terms of curvature, monotonicity, and sign, which are used to determine the sign of the the curvature of the composition. And as I said, this is the basis for many of these convex modeling systems. I made this website a long time ago. If you want to see more detail about this, I'd recommend it. But the essence of DCP is this simple composition rule, which tells you when a composition is necessarily convex. So suppose we have this composition where h is a convex function. Well, we know this is convex if for each argument I, h is increasing and fi is convex, or h is decreasing and fi is concave, or fi is affine. So that's it. That's the one rule. There's a similar rule for concave compositions, which is just the same rule. And this generalizes a lot of the sort of algebra rules for convexity that you would see in, say, the Boyd and Vandenberg textbook. And so it turns out this is really all you need to have a very effective type system for curvature. And one thing this also guarantees that I won't say too much more about is that you can convert the problem effectively into the standard form, which is a cone program. And so that's related to these sort of extended value, or these, it's called an epigraph transformation. Right. So this is the overall architecture for this conventional approach. So we have the problem expressed in the modeling language, which is converted into a canonical standard form, which is still an abstract problem represented by expression trees. So it's still a graph representation. But then it's converted into a sparse matrix representation, which is then passed to the solver, which does various sparse matrix factorizations and in general tries to exploit the structure exposed through the sparse matrix representation. So the standard form is the standard conic form that you've already heard a lot about. The idea is you have a linear objective, linear equality constraints, and then these nonlinear cone constraints. So this is just essentially a generalization of linear programming of non-negativity constraints. And it's sort of a surprising fact that pretty much any convex problem of practical interest can be converted into the standard form using only a few different types of cones. Essentially the non-negativity, positive semi-definiteness, SOCP, and exponential cone. And this is the general standard form for all these solvers. Okay, so the traditional solvers are mostly interior point. In terms of what's accessible through CVX-Pi, you have CVX-Opt, which is in Python. It's a standard primal dual interior point method done by Liev and Vandenberg and others. We also have Ecos, which is a more lightweight version that also supports the exponential cone. And that was done by Alex Domahidi. And we also have SCS, which is a first-order solver. So it takes a different approach that exposes more parallelism, or more potential for parallelism, which you can exploit through OpenMP and GPUs. And there are interfaces to many other things, many other solvers, all through this cone standard form, and also through this sparse matrix representation. So this has been a very successful framework for many years, primarily because these interior point solvers are so robust that you can really map just all kinds of problems onto them, and they'll solve your problem efficiently and reliably. And it's a reasonably portable architecture because the solvers are generally implemented using these linear algebra primitives like BLAS and LAPACK and sweet sparse for factorizing matrices. But as problems have grown larger and larger, this has started to break down. So I would say the limits of this are 10,000 variables, 10,000 constraints, or maybe 100,000 if you have a lot of sparsity. After that, it's just not a very feasible approach to actually factor these sparse matrices. And so at that point, using direct methods is really just not feasible, or at least it's not taking advantage of the sort of high-performance computing setups that people tend to use now. So as I mentioned, we do have some solvers that can use indirect methods. So SCS, it's a first-order method, and so it can use conjugate gradient to solve the linear system involving A instead of actually factoring A. And so that can get around this issue, but it turns out that the sparse matrix representation in and of itself can be problematic, and even converting into that form can be sort of computationally devastating. So an example is a lot of image processing problems involve FFTs or convolutions or various special linear operators that can be applied using some efficient method, But if you express them explicitly as a sparse matrix, you end up with something that is, at least in the case of the DFT, for example, completely dense. So you end up with this essentially quadratic representation for something that can be applied in n log n time. Right? So you can see at that point, even just constructing this matrix is going to completely eliminate the possibility of solving the problem efficiently. And I'll show you some examples of that later. And then, as I mentioned earlier, these solvers were designed with sort of an earlier era of high-performance computing in mind. And so they're not really set up to take advantage of GPUs and distributed optimization. And that's partly just a lack of implementation, but I think it's primarily and more fundamentally just a very, it's much more challenging to have sparse matrix factorization done well on these systems that are more reliant on simple parallelism than it is to do these first-order methods. And so in general, the modern high-performance computing situation is just much more amenable to these first-order methods. So what's the solution to this? Well, so the idea is we're going to swap out this sparse matrix representation for a graph-based representation. So the core data structure here is a computation graph. And so here, computation graph, it's a very simple idea. Here's an example. So we have this function, or this expression, x squared plus 2x plus y. And we have the variables as leaves, as inputs. And then we have a sequence of primitive operations that are represented as nodes in this graph. And these computation graphs are nice for a few reasons. I mean, for one thing, it's fairly straightforward to execute them efficiently in a distributed sense on GPUs. But also, it's very easy to, through simple graph transformations, you can also generate graphs for related operations that you want to carry out. So for example, computing the gradient of one of these computation graphs, that's just a simple graph transformation. Computing the adjoint, if it's a linear function, again, a simple graph transformation. And so it's a form that's very amenable to these first-order algorithms, or a data structure that's very useful for these first-order algorithms that rely on these computations. And perhaps most importantly, there's a lot of momentum behind developing systems for efficiently executing these computation graphs, because this is the core technology behind these deep learning systems. These are the core frameworks that people are using in TensorFlow and PyTorch and Theano Cafe and others. And so if we can build modeling languages on top of this, then we can leverage this pre-existing engineering effort. And what that gets us is immediately the ability to run these solvers on all kinds of different systems, ranging from standard CPU systems to multi-GPU to even on your phone. And also we're going to get the advantage of compilers for these things. All kinds of work is going into making these computation graphs efficient and scalable. So one drawback is that the support for sparse matrix factorizations and sparse matrix operations is not too extensive. It may have increased since I looked at it, but I think that's primarily just due to the fundamental challenges of making these really efficient on GPUs. So they do exist, but it's not the same performance that you would expect for other operations like dense matrix multiplication, for example. So interior point methods are not going to be particularly helped by converting to this framework. So this is really for problems where first order and indirect solvers are the thing to do. Okay, so the the diagram for this now is very similar. So we still have our problem that's canonicalized, still do a cone program in this case. And the only difference is that we've replaced this stage, which used to have a sparse matrix representation, with this computation graph. And that leads to a couple different changes in the interface. One is that we have more of a solver generator here. So essentially, given our standard form, instead of just constructing this graph, this matrix, what we want to do is construct a graph that actually encodes the whole solver. Right? You could just encode certain operations, but there's no reason not to just encode the entire solver as a graph. And then you pass this off to one of these frameworks, and it interprets it and then executes it on the platform that you choose. So here's an example of what I mean by solver generators. So essentially, you're just building a giant computation graph. And so you can decompose it into functions that generate the different pieces of this graph. So in this case, we have a function that generates the conjugate gradient method, given a function A. So basically, given this representation of the matrix A, that allows you to generate a graph, right, that represents multiplying A by some vector P. And okay, this is for symmetric A, but you would also imagine that you would have multiplication by A transpose. And then, given the vector B and some initial x, you just write out the conjugate gradient method, and this returns a graph, a subgraph that executes this. So this, in turn, can be part of a higher level algorithm. So you get this nice decomposition for your solver generator, and you don't have to worry about performance in particular, because this is all going to be executed by this runtime. So this is completely symbolic.
What is the graph? I didn't get that. The graph of the what's the graph of this algorithm?
Oh, so the idea here is that this is generating a computation graph to solve a linear system, A equals B with conjugate gradient. And so,
what's the computation graph? That's,
yes.
What are the elements? What are the nodes in the computation graph?
Well, so it's all these primitive operations that you see here, like the addition, multiplication, whatever, and then it's whatever subgraph is needed to multiply by A here. So this function call here is generating a graph that's embedded in this. I don't know if that makes sense.
But so the graph is the graph of the iteration of the algorithm.
Yeah, so you do have some, like a while loop operator and things like that. So it's basically the whole conjugate gradient method as a graph. So it has each iteration, and then it has something that checks if a condition is satisfied.
But that part of the loop would not look like an expression graph.
Yeah, that's true. So the conditionals are a little weird, but you can, they are.
But the iteration would be an expression graph.
Yeah.
You would get, but again, the key is that your whatever the graph for calculating that complicated operation, which was the matrix vector, is abstracted. It's whatever it is.
Yeah, exactly. Mm-hmm. And then this, in turn, it can be part of SCS or something like that. So we've implemented all this in CVXPy, or on top of CVXPy. So basically, it takes a CVXPy problem, and then it generates a TensorFlow graph to solve that problem. And it's using essentially SCS, so using an indirect method to solve linear systems. And then this is basically ADMM for cone programs. And so we ran some computational experiments to see how this compares using Titan X GPUs. So first, let's look at a lasso problem. So here, so we just had a standard lasso problem So we have a least squares objective and then sum of absolute value regularization term. And this is the CVIX pi code to express that. So it's just operator overloading. So you construct a variable, you construct the loss, you construct the objective here, and then you pass the problem into this CVIX flow library, which constructs this graph. And this is the results we get on a GPU for different types of A. So all these A's are the same dimensions, I think 6,000 by 12,000. And then they have different structures. So for dense A, we see on the GPU a large benefit over the GPU version of SES, so about 3x. And that's expected because that's sort of the operation that's like best suited for GPU execution. Sparse is actually slower, and that's for a couple reasons. One is that SES is designed with sparse matrices in mind. So if it does well at anything, it should do well at this. The other is that these TensorFlow and the other things like it, they're designed for a slightly different use case, which is problems that really take a long time to run, right? So you're training your neural net for a week or something. And so they have a reasonable amount of overhead. So this is 7 seconds to execute the whole thing. For TensorFlow, that's an extremely short runtime. And so there's an inherent overhead to this that for smaller problems can make it slower. And then we also have a convolution operator for A. And you can see this is what I was talking about earlier, where you have this situation where expressing it as a sparse matrix doesn't make sense. You want to use your ability to efficiently apply this operator. And you can see that there's, in this case, a smallish speed up over SES. So if we focus more on this convolution example, we can look here at a non-negative deconvolution problem. And so the idea here is that you have some noisy measurements of this convolution of a unknown signal x with a known kernel c. And you want to recover x given the prior knowledge that it's non-negative. So this is sort of very simple signal processing problem. And this is what the code looks like. Same idea as before. You construct your variable, you construct this objective, you construct a problem, and then you pass it in through this library that's going to construct this solver graph. And here, okay, this didn't come out very well, but you can. Okay, well, this is looking at the GPU solve time for standard SES, the GPU implementation, and then the TensorFlow version of this. And so this is solve time and this is memory. And unfortunately, you can't really see these numbers, but for dimension 100, so a very small problem, the TensorFlow version is actually slower, and that's due to that overhead issue that I mentioned. And that starts to improve as you go to n equals 1,000, so now they're about the same. And then when you go to n equals 10,000, suddenly this explodes. And this is partly due to the efficiency of the GPU implementation, and this is partly just an inherent difference in computational complexity that you get in using the sparse matrix representation versus using a implicit representation where you can only multiply by a matrix-free representation. So the sweet spot here is really large problems. So one thing that comes out of all this work that I think is really interesting is the idea of unrolled optimization. So the idea here is that we have some iterative solver. So for example, SCS, or something simpler like proximal gradient, whatever. We have some iterative solver that takes some initial point, some algorithm parameters, and applies the update rule again and again, okay, to solve this cone program that's defined by these values. And it runs until it converges under some criteria. Well, a variant of this is instead of waiting for this convergence criteria, you can just fix the number of iterations, which is actually that's something that's just quite common in practice, particularly in image processing. I've seen this. And then this becomes a very simply defined fixed function that can be auto-differentiated very efficiently, right? Since it's just a composition of some number of layers of this guy. And what we can do with this is a sort of bi-level optimization, where you have your fixed pipeline that solves this optimization problem, this cone program, at least approximately, and outputs a final iterate. And you take some higher level loss on that iterate, and then you use first order methods, which are well supported by this framework, right? These graph computation frameworks, because they're designed for auto differentiation. That's the whole point. So you can use all this functionality that we now have implemented to try and optimize, say, the algorithm parameters, or maybe something else. Like maybe if we have a lasso problem, we could try and do some hyperparameter selection using some sort of more complex algorithm. But I guess this makes the most sense when you are trying to optimize over a larger number of parameters than you could do with a simple grid search. And this is a active area of research. Thomas Pock has a bunch of papers on this now, if you're interested. I've done some work on this I can talk about offline. But I think it's very cool, and it's something that falls out of having these graph-based implementations of these solvers. So, in conclusion, I hope I've shown you that convex optimization is still an interesting topic, and that it's very simple to solve your convex problems using these modern languages. And you can solve very, very large problems using modern high-performance computing by exploiting these graph-based architectures and these computation graph frameworks that have been developed. And this is useful certainly for solving these problems, but it also sort of exposes some interesting research directions like this unrolled optimization. And all this is code that's you can download and try. Unfortunately, it's in Python, not in Julia. But we have CVXPy and then this CVXFlow, which makes these solver graphs. Yeah, thanks. Yeah.
So you only showed an example with one constraint in it. How easy is it to put a lot of constraints into this modeling layer?
Yeah, I mean, you can do as many as you want. So CVX, it literally just uses CVXPy, which you can express basically any convex problem, more or less. So you could have as many as you want. Yeah, I mean, there's some issues in terms of if you really had like thousands and thousands or millions of constraints, basically this whole system is sort of assuming that you have a vectorized problem, more or less. If that's not the case, it's going to be really, really slow. That's something I don't think that's inherent to the, like it could be fixed. It's just that we're leveraging these systems that are based on executing these massively parallel matrix operations. And so that's kind of what they assume you have in your problem.
Are there things known about convergence rates for these distributed algorithms when there's a lot of constraints?
Oh, well, I guess it depends what your distributed solver is exactly. I mean, if it's really like some distributed asynchronous thing, then I guess that would be maybe an open question. But I mean, I was thinking more about just using, executing standard algorithms just in a distributed way, and then synchronizing.
Okay.
So this is again sort of trying to address issues that come up with very, very large problems, where you might not even be able to fit it on a single machine. So I would say that, and then using GPUs more efficiently are the main benefits of this. And then these image processing problems and others where the sparse matrix representation is really not ideal.
But you've been looking at this kind of objective-based bigness, right? But you could think of like a two-stage linear program that has a similar structure. It could be huge.
You're saying put the constraints on the outer loop. Some of that.
Maybe. But I guess my point is there are classes like in robust optimization where the bigness is really just like the pile of constraints. The objective may be very compact.
Oh, I mean they're kind of symmetric in these solvers.
It's all epigraphs.
Yeah, it's all epigraph variables. I mean, it's all converted through epigraph transformations into these cone programs, and then it's like a primal dual thing. So there's really, yeah, I mean, it's I guess the complexity is more like the product or big small squared. So yeah, the complicated objective is the same as complicated constraints or large constraints for this particular algorithm. Oh, hey, sorry.
Okay, so let's stay within the conic programming paradigm for a second. So there was a paper that came out early last month. You talked a lot about first-order methods, but there's some guys at Carnegie Mellon who looked at taking SDS and kind of extending it to like a second-order method, and they called it a semi-smooth Newton method for fast generic convex programming. So I'm wondering whether you sort of seem to say that first-order methods are ideal for these graph structures are ideal for first-order methods, but could they also be used for second-order methods, just not interior point?
Yeah, so I probably, what I should have said is inversion-free methods. So really the question is, do you want to invert a sparse, or do you want to factor a sparse matrix or not?
Right.
If you do, then, I mean, you're going to be exploiting sparsity anyway, so it's not clear that there's any advantage to this. And if you don't, then I think this makes a lot of sense.
Okay. Second question.
Yeah.
Greedy. So, so you've talked about conic programming and how you can encode nearly all convex or all convex problems with a small number of cones. But that doesn't take into account the transformations, say from irrational power to a second-order cone problem, can increase the number of variables and constraints quite significantly.
Yeah.
So I'm wondering whether it's really desirable to use a small number of cones, first of all, and second of all, whether we should maybe break outside the conic programming paradigm altogether into just sort of convex set. You don't get the nice homogeneous self-dual embedding theory, perhaps, but maybe there's some generalization of that.
Yeah, I mean, I think that's a really interesting question, and I agree. I mean, if you're using first-order methods, if you're abandoning interior point methods, then I don't really think there's any particular advantage to the conic form. I mean, besides perhaps dealing with infeasibility in a nice way, through the homogeneous self-dual embedding, or other approaches. Yeah, and there are disadvantages. So this epigraph transformation, it introduces all these slack variables. And that's fine if you're solving the problem to high accuracy, right? There's really no harm. But if you're solving it to low accuracy, then you have these like chains of epigraph variables, and that can add up to an extremely low accuracy in the original problem. And so I don't think it makes too much sense to, unless there's really some clear advantage that you're getting out of the conic structure, like some clear acceleration method or something, then I don't really think it makes sense. And I agree with you. I think it should be something more general that stays closer to the original problem.
Do you know of anything? So the homogeneous self-dual embedding is nice because you can get certificates of primal or dual infeasibility, and PyReader, for example, needs that. But for just generic convex set programming, is there some nice notion that can give you some sort of certificate, primal or dual?
Yeah, so I've looked at this. Like, I had a modeling language that was sort of more what I'm describing. So it didn't do cone programs. It was for image processing. It was called Proximal. And for the problem, I guess for the problems that I've looked at, there really was it was not possible that they would be infeasible or unbounded. So it really wasn't a concern. So I haven't looked into that particular case.
Because Matt Wytock had that package. What was it called?
Yeah, are you talking about the Epsilon?
Yeah.
Epsilon?
Epsilon, yeah.
Yeah. It was yeah, that was very similar, yeah.
Right, and that didn't do it didn't do certificate. It didn't do infeasibility detection or unboundedness detection.
Yeah.
But it used this nice graph thing, and it wasn't conic. It had some cones, but it was just kind of epigraph set based.
Yeah, I mean, I think that's a good question. Yeah, I haven't really thought about that, but yeah.
Actually, we just made a paper in Oxford about certifying infeasibility for general conic programs without using homogeneous or dual embedding, only ADMM. So they might be. It's actually used in the QP solver I present tomorrow, but it's potentially very useful for also general conic programs. It's on optimization online if you
So what you call the solver generator, I would just call a solver. So the way you built it, it's very much tied into the modeling interface. But you could also think about it's a solver and the input is a data structure representing the graph. And the way it solves the problem is it uses TensorFlow.
Yeah, I suppose that's true.
How hard would it be to organize it? So, right, kind of like a standalone solver where it has some predefined graph structure as input, and then it does its thing to solve the problem.
Yeah, I think it'd be very easy because, I mean, these TensorFlow, these other things, they're almost like, I mean, they are embedded languages more or less, and so if you just write your thing within that language, right, you have some graph that represents, or you have something that, say, generates a graph for applying your matrix, like a callback, then, yeah, it is very straightforward. I mean, that's one, I think that's essentially what's happening here.
Okay, so it's not too tied to CVX5.
Yeah, it's more tied to in this case TensorFlow or whatever the graph execution thing is. But yeah, it's not really tied to CVX5 at all. You could provide any sort of like graph to execute those different operations. Yeah, so in theory, you could have lots of different modeling systems that all target this standard form. Yeah.
Has anyone thought about, instead of just first, second order methods, maybe like active set type methods, whether those might be parallelizable in interesting ways?
That's a good question. Yeah, I mean it's a little challenging. So tying the architecture to these deep learning frameworks is nice because they've spent like thousands and thousands of engineering hours making them work. But it does impose some constraints. So they're designed for first order methods. It's a little challenging to get them to efficiently do things that are more complicated, like to do more logical reasoning rather than just computing gradients and executing these graphs. Right? This does have some, conditional things. I think I showed that somewhere. Yeah, so you can do conditionals, but it's a little awkward. I think PyTorch, which is the new sort of hotness in this area, is much better about sort of dynamic graphs, so maybe that would be better suited, but I haven't looked into it that